In part 2, we're still looking at evaluating definite integrals. The difference here, though, is going to be that we have an inner function inside. So we're going to start by noticing 1 minus 2x is what our u should be, and we're going to work this two ways. We're going to do once with general, and then once with formal. So formal is that 7-step process. And if you've learned from another student who's in a Math 125 or who's had Math 125, maybe an engineering student, they may show you different ways to do that. And there's lots of different ways to do formal substitution. Just make sure that anytime you're working through it, you're not dividing by x. That's the key point, because it's very possible that x could be 0 in any definite integral. So let's go ahead and start with general here. Actually, both forms need u equals, so we're going to let u equal that 1 minus 2x. And when we take its derivative, du dx is going to equal -2. So the goal for general, remember, is to get the du dx sitting inside. So we can forget about that dinner. Remember, this is called dinner, derivative of inner. And then we can go ahead and just integrate. So the rule says this: if we have any u to a power, as long as we've got the derivative of that inner with respect to x sitting on the inside or even in the front, and integrating with respect to x, those dx's basically cancel and you're just integrating u with respect to u. So you can also get to the formal method from here, but I'm going to try to be consistent with what I've shown you in the other videos. All right, so we know that we have u right here, so let's go ahead and rewrite our integral. So we got 1 minus 2x, and then notice I left some space here, and this is squared dx. So when I look at what I have here, I've got my u, but I don't have that du dx part sitting on the inside. So in order for me to be able to get the green light to go, I've got to have a -2 sitting somewhere in that integrand. So if I put a -2, that breaks my equals, and I fix it by multiplying by the reciprocal, still negative though. So we essentially multiplied by 1. Once you get dinner, which is the -2, the derivative of the inner, sitting inside, then you can go ahead and forget about dinner and just go ahead and integrate the u to the power. And this one, -1/2, is going to stay in the front. So we'd have -1/2. The dinner goes away, and then we just add 1 to this exponent and divide by the new exponent. So we no longer have to put plus c. And notice right here, I left off my bounds and need to put those back in, 0 to 1. Because this is the command to integrate, and now we need the command to evaluate. So simplify this down as best you can. So 2 times 3. Or if you want to use the calculator, put the -1/2 in parentheses, divide by 3, and then do the second fraction to decimal. All right, so we'd have a -1/6, and then 1 minus 2x, the whole thing cubed, going from 0 to 1. So we're going to evaluate this with the fundamental theorem of calculus. We're taking the antiderivative, evaluating it at the upper bound, not necessarily the biggest, but it typically is. And then we're subtracting out the antiderivative evaluated at the lower bound. So doing that, we've got a -1/6. Let's make sure that negative goes along with that constant. And then 1 minus 2 times 1, the whole thing cubed. So that's the capital F of 1, and I'm going to subtract out the capital F of 0. So I've got the -1/6, don't lose your negative. And then plugging in 0, sometimes 0 matters, and here's one situation where it does. You don't always just get 0 there. So for this one, 2 times 1 is 2, and you're subtracting it, so 1 take away 2 is -1. But when you take -1 and cube it, you're also going to get -1. Now if you want to go ahead and change this minus a negative to a plus, that's good. So we're going to go ahead and combine those two things here. So that would just give us 1/6, and then 2 times 0 is 0, and that leaves me with a 1, and 1 cubed we know is equal to 1. So we have a negative times a negative, which is a positive. So 1/6 and 1/6 is equal to 2/6, or you can write that as 1/3. This one is also not geometric, so we would not be able to use a geometry formula to check our answer. For the formal process, you've done your first 2 steps, and your third step is always to multiply by dx. So let's do step 3. And then we want to look at the integrand that we have, which is the 1 minus 2x quantity squared. And I'm going to leave this as indefinite right now. I'm not going to put the bounds in there. So remember, our goal is different. We're trying to get substitution from steps 1 and 3 to eliminate any x's within this whole expression, including the dx. And dx and du are not usually equal to each other, so don't just put a du in place of dx. Alright, so this is u, so we're literally cutting that out and putting a u in its place for u squared, but we can't integrate u with respect to x. So what we have to do is, in step 3, we have to make it match what we need substitution for. So we cut that chunk out, it's u squared. When we cut this chunk out though, we've got to have that substitution from step 3 for just dx. Up here we have negative 2 dx. And that's going to end up with negative 1/2 du is equal to dx. So that dx substitution, dx is equal to negative 1/2 du. So dx is not just automatically a du. Okay, so when we write this out, we'll have u squared, and instead of the dx, remember we have the negative 1/2 and then the du. So I've kept everything indefinite up to this point. This is still really, though, your x bounds of 0 and, what was this one? 1? We can't integrate u's if we're looking at x bounds. So we also have to do a conversion over to u bounds. So we need a lower u bound and an upper u bound. So I'm going to put my x's in the order they occur. So the top is 1, the bottom 0. And then, so I can plug in 1 to my u function. Let's see, u is equal to 1 minus 2x. So 1 minus 2 times 1 is going to give me negative 1. And when I plug in a 0, I'm going to get positive 1. So this is a weird situation only because the upper bound is smaller than the lower bound. And that's fine. It's not a problem at all. There is a property that allows you to go ahead and switch it over. But we're just going to keep everything like it is. So for the 0 for x, we're going to put a 1 for u. And for the 1 for x, we're going to put a negative 1 for u. So the trick, if you want to switch these bounds so that it looks more normal to you, then you have to negate this integral right here and make it positive 1/2 u squared du. And then you can go ahead and integrate. But we're going to keep it as is. So we're going to leave that negative 1 up top. And we're going to evaluate. Oh, missing a step. Very important. We need to integrate this, right? So this is negative 1/2. I'm going to take u cubed over 3. And then the notation, the command changes from integrate to evaluate. And you're going from 1 to negative 1. So that's going to give me a, so I got a little ahead of myself there, negative 1/6, and then u cubed from 1 to negative 1. You've got f of negative 1 minus f of 1. So we plug in that negative 1, we're going to get negative 1/6 times negative 1 cubed. And then we plug in the 1, so in place of u. So you notice that the formal just takes away all that icky arithmetic over here. Okay, so it's a little bit harder for some people to get to that step 4. So let's go ahead and number our steps here actually. This was our step 4. And our step 5 was to integrate with respect to u. So that 7-step process actually becomes a little bit different after step 5. So normally in step 6, what you guys would do is plug the original u back in. But now we already got everything in terms of u, including the bounds, so we might as well use it to our benefit. So this is negative 1/6, and that's going to come out to negative 1. So negative 1/6 times negative 1. And then 1 cubed is positive, and take away a 6. So basically we have, oh, I think I missed a negative. So we're subtracting f of 1, got the negative 1/6, I forgot a subtraction sign. So make sure you get that subtraction sign in there. Alright, so negative, negative, then should be what? Not negative, but positive. So we've got a positive 1/6 in the first one, and positive 1/6 in the second one, which is going to be 2/6, or 1/3. So you're going to get the same result Just notice some of the arithmetic over here is a little bit easier. The second example in part 2 is very similar. The only difference here is we see a radical, really. The process will be the same though. So to rewrite, we're going to put 0 to 2, and we're going to bring that bottom to the top. So the 1 plus 2x squared. And then since we're bringing the radical up, it'd be the negative 1/2, and then dx. So we're going to have, let's see, we can go ahead and keep it like this for both forms, the general and the formal. And we're going to go ahead and let u equal for both of them 1 plus 2x squared. So that when I take the derivative of the inner function, du dx, I come up with derivative of 1 is 0, 2x squared's derivative is 4x. So over here, I've got my original integrand, and I should have left a little bit more space there, but we know that our goal, remember, is, so here's the trick for the general. If we have u to the n, and the derivative of the inner is sitting right next to it, and with respect to x, then that's essentially just integrating the u with respect to u. The dx's will cancel, you just have a du right there. And we know that that rule says we just add 1 and divide by the new exponent, typically plus c, but we're working with definite intervals. So in order to make this work for the du dx, I need to have a 4x sitting right next to it, which means I need to multiply by 4 on the inside, but I can only multiply by 1 and not change the equality. So I better be sure that I put a 1/4 on the outside with that 4 on the inside. So you've multiplied by positive 1, you've maintained equals from the original. So let's see what we have in colors. If you like the colors, we've got the u, and we've got the u here. And once you get du dx, you're home free. So du dx is 4x, and we have that right here. Du dx is equal to that. So we can go ahead and integrate with respect to that inner function. So this would be 1/4, and then adding 1 to the exponent, 1 plus 2x squared, adding 1, we get positive 1/2, dividing by the new exponent. And then once we've finished the command of integrating, we need to evaluate from 0 to 2. Go ahead and simplify your 4 times 1/2. Dividing by 1/2 is the same as multiplying by 2. 2 over 4 is equal to 1/2, or take the 1/2 of the 4 down here. Either way it works. But inside we've got 1 plus 2x squared to the 1/2 from 0 to 2. So when we go to plug in our upper bound, so using the fundamental theorem of calculus, we would have 1/2 and then 1 plus 2 times 2 squared, all to the 1/2, and then minus 1/2 and 1 plus 2 x squared. Oh, what's going to go in place of x? Plugging in 0 down here, this is the f of 0, and it's all to the 1/2. So we don't have to worry about the plus c, minus c, because they'll just go away, and then we can finish simplifying the arithmetic. So 2 squared is 4, times 2 is 8, and then plus 1 is 9. So you've got 1/2 of the square root of 9. Over here, we're adding in 0, so we just get the square root of 1, which is 1. So we're subtracting 1/2. And hopefully you know the square root of 9 is 3. If not, check your calculator. And 3/2 take away 1/2. You subtract the numerators, keep the denominators. So we'd have 2 over 2, which is equal to 1. So the formal process should give us the exact same result. But remember, it changes in step 6. So we just do the step 5 like normal, and then step 6 is where we've converted those u bounds over. All right, so for formal, these are my first 2 steps. Step 3 is always to multiply both sides by dx. And the goal is different. So let's rewrite the definite integral. So if I'm thinking of cutting these 2 chunks out, this x and this dx, I need to be able to replace them with an equivalent. And what I can do up here, if I just need x and the dx, which I have, with the exception of that constant, I can just divide by 4. So dividing by 4 on both sides would give me this expression for my step 3. So then I'm home free because I've got my substitution, what x dx is equal to down here. So cutting those two chunks out, we end up with 1/4 du. Now, remember these were x bounds, so we're going to talk about that in just a moment, but let's go ahead and keep this indefinite for now, u to the negative 1/2. And then for x dx, we need to put in 1/4 and du. And since we're going to do everything in terms of u, including the evaluating, we need to switch these x bounds over to u bounds. So we need this to be a u and this one to be a u. And I found the easiest way to keep track of this is just to keep them in the order that they appear in the integral. So for our first one, we got 2 on the top, so I'm going to put it first, and then 0 on the bottom. And we're going to let u equal the 1 plus 2x squared. That's what we called it up here. And so if we plug in 2 to 1 plus 2x squared, we get 2 squared is 4, times 2 is 8, plus 1 is 9. Then plugging in 0, we'd have 1 plus 2 times 0 squared is just 1. So even if this one comes out to be a smaller number, then you still can just plug in the upper bound minus lower bound. So I'm integrating with respect to u, and my new bounds are 1 at the bottom and 9 at the top. Adding 1 to the negative 1/2, I'd have u to the positive 1/2 divided by the new exponent. And now the command is to evaluate, and we're evaluating with u there. It's going to make the arithmetic easier. So taking 1/2 of 4 or multiplying by 2 over 1, we'd get 1/2. And this is just meaning the square root of u. So the square root of 9, when you plug it in, so we're going to do capital F minus capital F. And so we'd have 1/2 the square root of 9. And then 1/2 the square root of 1. And the square root of 9 we know is 3. 3 over 2. Take away 1 over 2. We're going to get the same result, 2 over 2, which is equal to 1. This is in part 2, but it is an application. We're looking at a company purchasing a new machine, and the rate of depreciation can be modeled by the equation below, where v is the value of the machine after t years. So we're asked to set up and evaluate a definite integral that yields the total loss of value over the first 4 years. So let's see why we need to do a definite integral here. And so if you think about the graph, so notice the restricted domain here from 0 to 5. And I'm going to do this one by 14 thousandths because I've got that big slope right there. So that 1 is equivalent to 14,000, and if I go down to -2, that's like 28,000. So you're just doing multiples of 14,000. So I'm just going to go ahead and go down to 7, 4, 5, 6, 7. And that's going to be my y-intercept. I could plug in t values, but I can also just think of this as the constant being out there and just look at the slope, which is really just equal to 1. So I could go up 1 and over 1, which is really 14,000 over 1, if you use the constant. And then up 1 and over 1 to 2. And then up 1 and over 1 to 3. And then up 1 and over 1 to 4. And then up 1 and over 1 to 5. Now, it's a little bit tricky because it does say the first 4 years. So from 0, 1, 2, 3, 4, and 5. So 0 to 1 is the first year, 1 to 2 is the second year, 2 to 3 is the third year, and 3 to 4 is the fourth year. So I'm only wanting to use bounds from 0 to 4 and not 0 to 5. So this one is a geometric shape. We could use probably the formula for area of a trapezoid, and that would give it to us, but most of us don't remember that formula, me included, so we're going to go ahead and use the calculus. All right, and the reason we're looking at total loss of value, the definite integral, remember, computes the net area. So that's why we're seeing that negative value popping up right there. Integrate 14,000 t minus 7, and this is going to go from 0 to 4. Keeping the 14,000 in the front, we really don't need to do a chain rule type of thing or formal u substitution because the derivative of the inner is just equal to the slope, which is 1. I'm just going to go term by term. So integrating the t, we've got t squared over 2. And then minus, we'd have 7t. We've already integrated, so now we're going to evaluate. I'm just going to keep 14,000 out here times this big expression. And so we'll be doing capital F of 4 minus capital F of 0. Plugging in 4, I'd have 4 squared is 16. 16 over 2 is equal to 8. Plug in 4, 7 times 4 is 28. Keep on going, plugging in the 0. Notice that we get 0 over 2 minus 7 times 0, so we just get 0 right there. So we got 14,000, and 8 take away 20 is times, whoops, I left a little bit big of a bracket right there, sorry about that, just ignore that. Alright, so we've got 14,000, and then times is 8 minus 28, which is negative 20. And if you do the calculation there, that's going to give you negative 280,000. So that's the total loss of the value, but if we're thinking of it in terms of the word loss, that's really a double negative. So if it says in sentence form, the total loss over the first 4 years is going to be a positive $280,000. So that's what we would actually state if we were writing it in like a sentence form.